Hello there, young students of chemistry. This is a quick recording to give you some information about the tool for your mind, the periodic table of elements. This is an overview, so we're not getting into the nitty-gritty. And then we're going to talk about atomic structure and how we can use our periodic table to determine the number of protons, neutrons, and electrons that are in an atom or an ion. So if you consider the periodic table, on the left-hand side of the periodic table are the metals. And just by knowing an element's position on the periodic table, you can know the properties of that element. So we know that metals are solid at room temperature. With no exceptions except the metal mercury. Mercury is a liquid metal at room temperature. Metals are good conductors of heat and electricity, so metals in their solid state are electrolytic. Metals are malleable and ductile, and if you don't know what that means, malleable means you can just form it into the shape that you want. Think of people who do statues with metals. Ductile means we can draw it into a wire. Think about taking a piece of chewing gum and stretching it. That is ductility. And they are lustrous. Lustrous means shiny. So metals that are not oxidized are shiny on the surface. Now, we know that non-metals, the prefix means not. So non-metals do not have the properties of metals, meaning that at room temperature, instead of being solid, they're usually liquid or gas. They're not good conductors. The opposite of the word conductor is insulator. So non-metals are insulators. The opposite of malleable and ductile is brittle. And of course the opposite of lustrous is dull, not shiny. So that is a summary of the properties of metals and nonmetals on your periodic table. Okay, so just to be clear, this is a periodic table, and the dividing line for metals and nonmetals is this line here that goes down the left of boron, across the top of aluminum, down the side of aluminum, across germanium, on top of antimony, down the side of antimony, across polonium, and so on, down the periodic table. So this stair-step line separates metals from nonmetals. Anything to the left of this line is considered a metal except for hydrogen. Hydrogen's a strange little element that can do all sorts of weirdo things. So some periodic tables actually have hydrogen over here. And that's okay with me. Hydrogen can behave as the elements in the fluorine family, or it can behave as the elements in the lithium family. Its properties are closer to that of the fluorine family. It has, it's a gas at room temperature, stuff like that. So anything that's touching the stair-step line here is something that we call a metalloid, except for aluminum and boron. So silicon, germanium, arsenic, antimony, tellurium, polonium. These are what we call metalloids. Now, a metalloid has some properties of metals and some properties of nonmetals. So it's not like saying it's a metal and a nonmetal at the same time. But if you think of the element silicon, silicon has the ability to conduct electricity. That's what the motherboards and in computers are made of. However, it's very brittle. So that's a property of nonmetals, while the conductivity is a property of metals. But it's also very shiny, which is a property of metals. So silicon has some properties of metals and some properties of nonmetals, and that's how we define a metalloid. There are some groups on the periodic table that I want you to know the names. So these A groups are called the representative elements. That would be any element that is in one of these columns here or one of these columns here. Those are called families or groups. So any one of those are called the A groups, the representative elements. When I say A groups, it's because we typically use this system where this group is 1A, this group is 2A. So they're the A groups. This group would be 3A. And that really gives you some information about how those things bond, which is why we use that. So I do want you to write this down, even though you don't understand it quite yet. But A groups are elements that have electrons in their S and P sublevels. Here are some names I want you to know. The alkali metals are family 1A. That's the family that hydrogen is in. The alkali earth metals are family 2A. That's the family that starts out with beryllium and magnesium and calcium and strontium. And then the halogens are family 7A. That's the family of nonmetals that starts with chlorine, and you've got chlorine, fluorine, chlorine, bromine, iodine, etc. You may have heard of halogen lamps. Think about that one. And then the noble gases, family 8A, also called the inert gases. These are nonmetals, gaseous nonmetals that are unreactive. They do not form compounds in nature. We can force them to form some compounds, but typically in nature they're not formed. They're not found bonded to anything else. Transition metals are those B groups. So if you look on your periodic table, it's taking all my stuff away. If you look on your periodic table, that's this section in here. These are the transition metals. And then these two rows down at the bottom are called the inner, I-N-N-E-R, transition metals, because the truth is they kind of plunk up right in here, and they would shift the periodic table over to the right a little bit. So transition metals, and then the lower two inner transition metals. Let's give it a minute to do this. What's cool about the transition metals is they have, so the transition metals are weird because they can change their number of valence electrons. They have this big d orbital, and because of this, anything in the, I shouldn't say anything, but almost anything in chemistry that has some kind of bright color like blue or green or yellow, it has a transition metal in it, and that's because you have electrons moving around in that d sublevel from the S to the D, and that's a really easy move to make, but when they move, it produces color. You'll learn a little bit more about that later. So take a minute and write, because of the D block, the D block, and the number of orbitals in that D block, but we'll discuss that in length later. Okay, atomic structure. This is the stuff that makes up an atom. We have protons, and if you look at your periodic table, protons are the atomic number. On the periodic table that you will have, that atomic number is at the top of the box. It's the whole number. So it doesn't really matter where in the box on the periodic table that number is. It's the whole number that tells us the number of protons. Now, because atoms are neutral, the protons are equal to the electrons as long as it's not an ion. So there's two types of ions, positive ions and negative ions. We call positive ions cations, and negative ions are called anions. So when a cation forms, this is an atom that has lost electrons. So we have more neutrons in the nucleus than we have electrons in the electron cloud, and that makes that atom now have a positive charge. We no longer call it an atom, we call it an ion. A negative ion forms when an atom gains electrons into its electron cloud. So now it has more electrons in its electron cloud than it has protons in its nucleus. So that gives it an overall negative charge, and we no longer call it an atom, we call it an anion. So protons can never change. The number of protons in a nucleus is set, but the number of electrons does change. So in order to have a positive charge, we have to have more protons than we have electrons, and to have a negative charge, we need to have more electrons than we have protons. So we can say that magnesium atom, neutral, versus magnesium ion, that's a charge of 2+, that has lost 2 electrons. Oxygen, the atom, is neutral. Oxygen, we call the ion, we call that oxide, has a negative 2 charge. It gained 2 electrons. And then to calculate neutrons, mass number minus atomic number will give us the number of neutrons. Okay, so at this point you should transition over to the notes that you have in your binder. The top of it looks like this. You can see what we have here are two ways that we're going to designate isotopes. Okay, so what we have here, this format that's in this box, is called the AZ format. This was just writing 2 seconds ago. Okay. Let me pause. Okay, different program. So here you can see what we have is this format where you have the symbol of the element, and then over here to the left you have some numbers, the atomic number and the mass number on top, the atomic number on the bottom. And what that is saying, this format is called the AZ format. Z is, sometimes they'll identify an element by its Z number. Its atomic number is the Z number. So we have A above Z, mass divided by atomic number. This is another way of indicating an isotope. And here we have the symbol of the element or the element name and the atomic mass. On this you'd have to get the atomic number from the periodic table. So remember that the number of protons is equal to the atomic number. The number of electrons is equal to the number of protons, assuming we have an atom. And then the number of neutrons is the mass number minus the atomic number. So I'm going to do a couple of these with you, and then I want you to finish out this chart. So on this chart here with hydrogen, we're not given any information about the hydrogen in this chart, but we can see from our periodic table that we can get the atomic number of hydrogen. It's atomic number 1. It's a whole number, right? And we can get the atomic mass again from the periodic table. And its atomic mass is 1.008. Just looking at your periodic table. I might have a different periodic table in front of me, but 1.008. You can use the one from your textbook. Now the mass number is just the atomic number rounded to a whole number. So the mass number for hydrogen atom is 1. We know that protons are equal to the atomic number, right? So the number of protons are 1. Neutrons are mass number minus the atomic number. So 1 minus 1 is 0. And electrons, because this is an atom, and we know that because there's no charge written out to the right, protons equal electrons, so there's 1 electron. This hydrogen is a cation. So this is not an atom. It's got a little positive symbol right there. Still, the atomic number never changes for hydrogen. The mass from the atomic mass is not given, so we'll get that from the periodic table, and then we'll round it to get the mass number. Protons are 1. Neutrons are still 1 minus 1, 0. The electrons have changed. Before we had 1 electron, but we can clearly see from this positive indicator that this hydrogen atom has 1 more proton than it has electrons. So if it has 1 proton and it has 1 more proton than it has electrons, that means it has 0 electrons. This third hydrogen is an isotope of hydrogen. The atomic mass is different. So instead of having a mass of 1, because the mass is given right here, we're not going to use our periodic table mass. We just know that the mass number is 2. The number of protons are 1. Neutrons, 2 minus 1 gives us 1. And because this is not a superscript with a charge, then we know that this is a neutral atom, and protons must equal electrons, so that is 1. Here's an isotope in the AZ format. We don't need our periodic table for this at all. We have everything we need. The 16 is the A number. That's the mass number. The 8 is the Z number. That's the atomic number. So we don't need our periodic table for that mass at all. We're told that it's an isotope that weighs 16 atomic mass units. The number of protons equal to the atomic number 8. Neutrons, 16 minus 8, atomic mass minus atomic number. That gives us 8. Now the electrons here, we have a 2 minus charge. What that is telling us is that there are two more electrons than there are protons. And since we have 8 protons, that means that we have 10 electrons. I'll do one more and then I want you to finish this up. So sodium, again in the AZ format, we have the atomic number 11 is given by the Z number at the bottom. The mass number is 24, given by the number at the top. Protons are equal to the atomic number 11. Neutrons are 24 minus 11, so 13. This is a neutral atom because there's no charge written as a superscript like there is here. Since there's no charge up there on the right, we know that protons will equal electrons. Okay, if you will pause the video and finish that chart, and then I want you to come back and check your work. Don't be a slacker. Do it yourself and then check. Okay, and we're back. So take a minute to check your answers. Jot down any questions you have so that you can ask me when we get back to class. And you might want to just pause this now so you can check your answers. And that is all for this recording. Thank you very much.